Power rule! We are all familiar with the power rule. It allows you to easily... Yann, be quiet, you have a squeaky chair. It allows you to easily find the derivative of algebraic expressions by multiplying each term by the exponent on that term and then decrementing the exponent. For example, the derivative of the function x to the fourth is 4 times x to the third. But here's an interesting question. Why can we do this? What magical math person figured out that multiplying terms by their exponent and decrementing the exponents would give you the slope at a given point?
To understand why this works, let's look at the limit definition of a derivative. If you don't remember it, the derivative of any function f of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Let's see what happens when we plug our example function x to the fourth into this definition. We now have the limit as h approaches 0 of x plus h to the fourth minus x to the fourth all over h. To evaluate this limit, we first need to expand the binomial x plus h to the fourth.
In binomial expansion, we start with simply the first term, x, raised to the full exponent, in this case, 4. Each successive term is constructed by decreasing the exponent on x by 1, while simultaneously increasing the exponent on h. So the next terms would then be x to the third times h, followed by x squared times h squared, and so on until we end with a single h to the fourth. However, all of these terms also have coefficients on them that we have yet to find, and these coefficients come from Pascal's triangle, the triangle of numbers constructed by adding up the adjacent numbers in the previous row. In this case, because our binomial x plus h is being raised to the fourth power, our coefficients will come from the row of Pascal's triangle, whose second term is a 4, shown here in blue. Adding these coefficients onto each term, we now have the full binomial expansion of x plus h to the fourth. In the coming shots, we will not include these coefficients simply because there wasn't enough room on the Lego board, but keep in mind the coefficient on this second term with only a single h, and where in Pascal's triangle the coefficient came from.
Substituting the expanded binomial back into the limit expression, and keep in mind that there are coefficients on many of these terms, we discover that, first of all, these two x to the fourth terms will cancel out. Next, we have an h in all of the terms on the top, so we can divide them out and get rid of the denominator. Note that the exponent on h in all of the terms on the top has decreased by 1 in each term, meaning that the term that previously had 1h now has 0, while all the other remaining terms have at least 1h in them. Because the limit is bringing h close to 0, all those other terms that still have an h in them will also approach 0 and will become negligible. We now have a single term, the second term, in the binomial expansion, and its coefficient is 4. No matter what exponent you raise the binomial x plus h to, there will always be a single term remaining, and it will always be the term that had a single h in it after the binomial expansion. If we then go back to look at the expansion process, we will find two things. Firstly, the coefficient on x will always be 1 less than the original exponents, since we decrease the power of x by 1 to get to having a single h in the term. Secondly, the coefficient on this term will always be equal to the second number of the corresponding row in Pascal's triangle, and the second number in any given row in Pascal's triangle will always be equal to the original exponent. For this reason, the derivative of any algebraic expression can be found by multiplying the term by the exponent and then decrementing the exponent. To understand the derivative of exponential and logarithmic functions, let's again look at the limit definition of a derivative, which is the limit as h approaches 0 of f of x plus h minus f of x all of
All over h.
all over h.
Yeah. Yann's really smart, everybody.
Oh yeah. Okay.
I'm leaving this in, you know.
Okay. If we now look at this definition with the exponential function e to the x, we have the limit as h approaches 0 of e to the x plus h minus e to the x all over h. So bad. Using the properties of exponents, we can turn this into e to the x times e to the h minus e to the x all over h. We can factor out an e to the x out of the top two terms and then out of the limit, leaving us with e to the x times the limit as each h approaches 0 of e to the h minus 1 over h.
The number e has many different definitions, one of which is the number that will make this limit expression equal to 1. For this reason, we can simply say that this limit is equal to 1, and the derivative of e to the x is simply e to the x. Now that we've proven that the derivative of e to the x is e to the x, we can find the derivative of the natural log of x using the fact that these two functions are inverses. The derivative of g to the x. What? Aha, we never finished that paragraph.
Yeah.
I'll improvise. This is off script, everyone. The derivative of g to the x, if you're given that a function f of x and g of x are inverses, the derivative of g to the x can be given by 1 over f prime of g to the x. That's true? Yes, that is true. Since these two functions, e to the x and natural log of x, are inverses, the derivative of the natural log of x is equal to 1 over the derivative of f of g of x, which is 1 over e to the ln of x. Which is what, Jan?
Was that not mine?
Which is 1 over x. Aha! Alright, Jan's turn.
So we've got to the point where it's 1 over x, right?
Yes.
Yes, good. So I'll just take some of yours since you took some. And since we know that e to the ln of something... Oh, no, never mind. Since we know the derivative of f of x is e to the x, we can now replace the f...
Oh yeah. Okay, keep going. Sorry.
Where should I start? No, we did...
Let's just do this one live.
Should we do it live?
We could. I think that'd be better. And be easier to explain things.
Okay. We'll do this one live.